afternoon, everyone. Thank you for staying. I'm very honored. Yeah, I'm very honored to be here. This is what I belong to. So I'm the coordinator. My name is Benoit Herman. I'm from Belgium. I'm the coordinator of the Louvain Bionics Research Center, which is amazing as a job because I coordinate 30 professors. Most are surgeons, NDs, but also neuropsychologists, physical therapists, and engineers who work together for understanding motion and then assisting motion. Assisting motion for the patients, for example, we have prosthetic limbs, we develop exoskeletons and rehab robotics, but also surgical guidance, for example, replacing the aortic valve on baby heart and the like. So I'm very happy to do my job, and part of my job is also to, as an engineer, to train PhD students. And one of my PhD students is working on microsurgery. This is exactly why I'm here. And the question we try to solve is, could we make microsurgery both accurate and fast? And the project was initiated by Professor Langelet, who is quite known for facial allograft and transplants. And basically, when you look at robotics to increase accuracy, one way to do it is, for example, to do co-manipulation. It might not be obvious for you, but there are different kinds of co-manipulations. The first kind is you have a device in hand that is itself a robot, and then it will measure the way you move, filter what has to be filtered, and then just actuate, for example, the needle. This is the case of this Micron device from Cameron Meiji University that's actively moving this against your motion to stabilize actively. And that's one way of doing. The other way is having a robot holding also the tool you hold. That's parallel co-manipulation. And this device is the steady hand, for example, from Johns Hopkins University, which they are now outsourcing for different applications. One is ENT, and you see that the robot is there, and it's basically damping your motion. So it filters the motion to avoid unwanted motion and just to let regular and wanted motions go. And when you look at how it works, it's basically, as I told you, a damper. And when you look at this setup, you will see the difference between handheld, purely manipulation, and co-manipulation. And you will see the advantage, obviously, of co-manipulation. The motion is very smooth, there is no contact with that, while with freehand, obviously, you have contact, it shakes a lot, but it's much faster. The surgeon makes mistakes, he hits the target multiple times, but during the time he did it once, manually with it too. So it has a cost in terms of time. There's another way to help surgery, and we still believe that for eye surgery, co-manipulation is fantastic, but for 3D stitching and the like, teleoperation is still the way to go. And so, obviously, you all know this kind of devices. This is an historical first version, first prototype, just to mention. This is remote teleoperation. The devices you've seen, and you will see again later, is direct teleoperation, I would say. The surgeon is standing or sitting just in front of the patient, looking through a microscope, just like in this case, the Robotal device, which is a robot for middle ear surgery. And basically what we did is to take this idea from our colleagues from Paris, which are also involved in the research project I'm talking about. And we decided to adapt these ideas to microsurgery. So we designed a robot with a few design choices. The first one is that it has 7 degrees of freedom. Obviously, it has to move in space for making deep flap, for example, and the like. So open microsurgery. 3 for positioning and 3 for orientation. But we decided to decouple them because you need very high accuracy in positioning, but the dexterity of the hand is quite good for rotation. So we decided to start from a completely decoupled device where you have 3 linear motors in series and then 1 remote center of motion device that can just turn the instrument around 1 single point. That's it. To do that, first we had to design from scratch robot, and the first step were kinematic measurements of actual microsurgery, microanastomosis, dissection, and the like, using 3D instruments, tracking a scene camcorder to see what are the different steps, and obviously recording the microscopic scene because it's still under a microscope. And from that, we could set the basics of what should the robot be able to do. You see these kind of velocities, the workspace that is mostly used for a microanastomosis, the rotation, speed, and the like. So that led us to design a robot correctly. So we, as engineers, we did maths on that. We love maths. You hate, I know why. But so we ran optimization algorithm to avoid the robot hitting the patient, the surgeon, the microscope, the other robot, because it's by manual telemanipulation. And we ended up with this first prototype, which is by far less advanced than the prototype 2 that you will see there. But let's call it the prototype -1 of our lab. It's a teleoperation. This is already a quite old video. It's a 10-month video. You see there is still a huge lag. So we spent the last 10 months having a good control of the robot. And the purpose of this is now to try to solve this problem of speed versus accuracy. Because when you look at this recording, this is the vessel location, and this is the trajectory of the major hand instrument tip. You see that the range of speed goes from 0 to 180 millimeters per second. When you split that into low speed, mostly around the anastomosis site, and high speed when you go a bit further, that makes us think of a big problem. And the problem is that most telemanipulators, mostly the Da Vinci of course, uses a constant motion scaling factor. When you need high accuracy, what do you have to do? You need to have a high scaling factor, because then it will decrease the tremor and it will decrease the motion, so you can increase the accuracy. Very fine. So more than 10 to 1 down scaling factor would be very fine. So the hand velocity is reduced by 10, and velocity is important. But when the instrument requires a travel of 10 centimeters, it means with this constant fixed scaling factor that your hand has to move from 1 meter. This is why you need declutching, recentering, declutching, and that's still a problem. It disrupts surgery and it makes it slow. Just because not the robot is not capable, but the interface is not capable of having adaptive velocity. So that's a problem, because telesurgery is usually slower than conventional surgery, laparoscopic surgery or open surgery. And it's a big problem for many reasons. For all reasons, you know, for pressure in UR and the like, but in terms of free flap transfer, it's also a problem with the graft salvation. If you take too much time, you will lose the graft. That's also a big problem. So we need to find a way to have high accuracy at some moments and high velocity at other moments. So the purpose of research is to try to design adaptive motion scaling factors. We have reviewed the literature, and there are many different approaches existing in multi-scale teleoperation. It's not new. It's new for surgery, but it's not new for space applications, for nuclear applications, for microassemblies. So we have background on that. One idea is, for example, to have one region around the anastomosis where you need very high scaling factor, so you are very accurate and very slow. But the further you go, the faster you go too. That could be one possibility. It has drawbacks. For example, should it be region by region that the scaling factor change? But what happened at the borders between regions? So that has to be tuned. That's one possibility. You could also have a scaling factor depending on the instrument motion direction. For example, when you operate under a microscope and you need to pull on a thread, you usually pull vertically. And at that moment, you do not need any kind of accuracy. You need smoothness, but you need velocity. So we could differentiate between in-plane and local motions and upwards motions, which could be much faster because they are less dangerous. That's an option that has been investigated too. One possibility too is to have a kind of velocity constraint. If you move slowly your joystick, we can understand that you try to become as accurate as possible. So we will further decrease the velocity of the robot. The moment you move fast, we understand you want to move fast, so we will further increase the speed of the robot. So we could have an adaptive strategy depending on the velocity of the hand, not only on the position of the instrument. That's also a possible way of solving this problem. And there are many combinations of these strategies. There are also strategies to push back the limits of the workspace. For example, when you arrive at the border of the workspace, then you keep pushing and you will completely change from a position to position control to a position to velocity control. Just like when you push on the gas pedal, the further you push, the faster you go. So you could have a different mode on the borders, so you don't have to declutch and reclutch. But these are also very difficult to master, we believe. So we should try that, and that's the purpose of the robot. We will also try maybe simple things as that. You have direct control of the velocity or of the scaling factor. You don't press the pedal, it's 10:1. You press maximum, it's 1:1, and it's continuous, so you can adapt online. Maybe everything I've said is stupid because that will work. We don't know, and the purpose is now to compare that, so to implement that on the robot, and to try these and more, and hopefully next year my PhD student will be in Africa to present the results. Thank you very much.